This is part two then, welcome back. The timing of an electric kettle. What I want to show you here then is the more stable versions of the graph that I drew using Excel. And I'm also going to compare that with the graphs for experiments 2 and 3. And you'll see, I won't do everything that I did, but you'll see some predictions I've made using polynomial order 5 and linear estimation regression equation, ordinary squares. And then we'll have a look at the residuals, see how they behave. And remember, whilst essentially we're making a forecast, we can't go beyond 0 time and we can't go beyond 100 degrees because that's the limit of boiling water at sea level anyway. Therefore, we're only going to think about interpolation, not extrapolation. Otherwise, you'll see it's fairly straightforward. Polynomial order 5 is a little bit tricky in some respects, not impossible, and Excel can estimate them very easily with linest and with the trend line on a graph, but also going to introduce the statistics where statistically I'm comparing experiment 2 with experiment 3 because the results are a little bit different, but actually statistically are they equivalent? And you'll see what that means as well. But that's it then, that's what to look forward to. Relatively advanced from something as trivial as boiling a kettle. So let's crack on with that then. Well, here's the graph that I drew for kettle 1, the first experiment. You can see time in seconds goes up to 120, and then on the vertical scale from 0 to 120 degrees centigrade. Of course, it stops at 100 degrees. And what do we find? It started here at 18 degrees. The reason being 18, not that it was freezing cold where I was, but I took some water from the fridge and it drove the temperature right down. That's one of the reasons why I did experiments 2 and 3. And then as I switch the kettle on at point 0, you can see what's happening. Virtually flat line, and it increases. You can see that it's a little bit jaggedy. That's probably because of the way that I took the timings already from the graph. And if I did this that little bit more accurately to 2 decimal places, it would probably be a much smoother curve. But anyway, there it is. It's virtually an S-shaped curve. The interesting thing will be what happens with experiments 2 and 3. Do we get the same curve? But notice at 94 degrees, the kettle, you might hear it on the sound, the kettle switched off automatically, which is about 95 seconds, but it continued to warm, to heat, until it got to 100 degrees. Here's the polynomial order 5 equation that I got from this graph, and you can see the green line behind the actual and the polynomial estimation now. It's a pretty good fit because r squared is 0.9993. And if we do any interpolation, we're not going to extrapolate beyond here and beyond there and even down to the bottom. We're not going to pretend that we're going to start the kettle at -5 seconds or we're going to boil the water to 115 degrees. We're not going to do that. So my equation, which is this one, with this r squared, it's a pretty good fit, isn't it? I then did some calculations. I mentioned in video 1, I made some predictions using this formula. Let's call it a model. And there we are. When the actual temperature is 18 degrees at time t is 0, this model is predicting 18.51. 13 seconds, 19, 17.23. You can probably see that, by the way, down here, where it's, let's call it the worst part of the graph. But as we motor along, 24, 23.89, 25, 24.57, and you can see the residuals. If you plot the residuals against your predictions, look at what you get. Nonlinear, and another nonlinear element. Are they linear elements, or is it a continuation of this, a continuation of this? But it's not randomly drawn as we always expect with residuals from regression equations. But never mind. I also did ordinary squares. And actually what I did was at every time point, I created the intercept and the slope for no real reason, because I could do it. And the final equation right at the end, I don't show on this graph, but it's a valid equation. And here we have now then 13 seconds, actual 19, prediction 19. Actual 22, prediction 21.1. Actual 27, prediction 25. And here's the residuals. Again, not a straight line. Are we expecting a straight line with an S-shaped curve? Probably not. But that's what I found. Experiment number 1. I've come to Excel now to explore Kettle 2, what I've called Kettle 2, Kettle 3, experiments 2 and 3. And I won't show the whole diagram, the whole data I should say, but here's the polynomial order 5 for Kettle 2, experiment 2. Can you see the shape of the graph? Does it remind you of anything? Found this by means of the trend line, right-click, trend line, polynomial order 5. And this one is polynomial order 5 using the linness function, which you can just about see there in the formula bar. And all you do is you do y, x's, and then to the power of curly brackets, in this case 1, 2, 3, 4, 5. I also created the ordinary least squares linness function down there. And we can see the effect of that. What I'm interested in, of course, are two things. First of all, what do the residuals look like? So I've created the function and the polynomial, predictions against residuals, actual against residuals, linear prediction against residuals, and actuals against residuals. And you see something very similar to what we had with experiment number 1. Let's look at Kettle 3, experiment 3. Again, look at the line. We must be starting to see now that when you boil a kettle of water, whether it's half full, a quarter full, or got an exact amount in it, the curve looks like this. Sample of 1, only 1 kettle, of course, but 3 experiments. And what do we find? R squared 0.9994, very similar to what we had with the experiment 1. And poly order 5, linnest, ordinary least squares, linnest. Again, on the left-hand side is all the data. But now the residuals, polynomial, a bit different, don't you think? And linear, again, a bit different. What do we conclude from that? Well, nothing really, because remember, all the data is contained in 0 to 100 and something seconds, and from 0 to 100 degrees. It's going nowhere else, but it's non-linear, and so you do get non-linear residual. What I've done here is I've set all the regression equations against each other on the R squared. You can't tell a great deal because they're in scientific notation, but they're all very small numbers over here. But intercept 18.5. I'm really interested in these two, experiments 2 and 3. Intercept 33.2, intercept 33.5. Very similar, different data set, very similar. And the numbers, well, no, they're not the same. They're fractionally different. They are very small differences. And with OLS, what do we find? R squared for the polynomial, very high. For the linear OLS, they're high, but not as high as this one. Numbers minus here for the intercept, 14.5, 16.5, 0.97, 0.866, 0.82. There we are. By comparison, the final thing I did was I made a note of the time in seconds for experiment 2, and then again for experiment 3, and I use the t-test to sample assuming equal variances utility from the data analysis tool pack. You do that, series 1, series 2, it gives you all of these values, all of them. And my null hypothesis was that the means between the two are equal. The alternative hypothesis is that the means between the two are not equal. So in this case, I set it up for the hypothesis has mean difference of nothing. And in the end, using this two-tailed test. If E17, this one, is less than 0.05, then we reject, otherwise we accept. And similarly, taking E14 greater than E18, 14 and 18. If E14 is greater than E18, do not reject the null hypothesis, otherwise you do. And in this case, we accept the null hypothesis and we reject it. And in both cases, the conclusion is the same, that the means are the same. Different test, same answer. I did one as well, assuming unequal variances. I hypothesized that the mean difference would be 5, but in the end I got the same answer, that the means are the same. Okay, there we go. Well, that's what I did. You boil a kettle and you get all this out of it. I hope you find it interesting, and you can take this Excel file, by the way. I'll try and link to it in the, no, I will link to it in the notes of this file. And well, good luck. Any comments, I'd be pleased to hear them. Thank you. Duncan Williamson, as always. Goodbye.